Hi everyone, welcome. My name is Antal, and in this video I would like to have a look at how the two-term parameter shift rule can be derived using the Fourier representation of an expectation value. Let's jump right into it. If you are not familiar with parameter shift rules, I recommend that you check out our video on how quantum gradients can be computed on hardware. Also note that in this video we will be using the notation that was introduced in the video on how expectation values can be written as Fourier series. What is special about quantum gates that admit the two-term parameter shift rule is that they will have at most two unique eigenvalues. What this means in practice is that they will have a single positive unique difference when we create the positive unique differences for the gates. So what we can write is that there is going to be a single uppercase omega such that this uppercase omega is going to be equal to omega 1. What this amounts to is that if we have the expectation value Ex being the expectation value of some operator B, and we write it as the Fourier representation of we write the expectation value in a Fourier representation, then we will only have a single A1 coefficient such that we have omega cosine omega x here, and then we have B times sine omega x here. So once again, just to summarize, for some unitary gate where we have a single positive unique difference of the eigenvalues that generate that unitary gate, we can write up the expectation value Ex as we have seen in the Fourier series representation of expectation values video by having one coefficient for AL and BL, and this will be our Fourier series that we are looking at. Well, if we have this representation of the expectation value, we can derive the two-term parameter shift rule manually. What is meant by that is we can write up three equations and then transform those expressions that we've obtained by writing up these three equations, and then we will obtain the parameter shift rule for two terms. First off, let's introduce a shift term S such that this is going to be a real number, and we will also restrict ourselves just that we can later divide by an expression in our derivation, such that omega s over pi is not going to be a natural number. Once we have this notation in, I will just quickly outline the steps for the derivation. First off, we will write up what Ex plus s is going to be. Then we write up what Ex minus s is going to be, knowing that Ex is equal to this expression. Then we consider the derivative of Ex. And if we have these three equations written up, then by some reordering, we will get the two-term parameter shift rule. All right, let's first start by writing up the first equation. What we had was Ex plus s, which we can just simply write up by substituting into the original expectation value equation. We will have A0 plus A1 cosine omega x plus omega s omega s plus b1 times sine omega x plus omega s. This can be further expressed as A0 plus A times, well, here we can use trigonometric identities for this term as well as for that term. So what we will have here is cosine omega x times cosine omega s minus sine omega x times sine omega s plus we will also have b1 times sine omega x omega x times cosine omega s plus cosine omega x sine omega s. Similarly, we can also write up the second equation, which is going to be e x minus s. At this point, it may seem a little bit confusing, but what we would like to then compute is going to be 1 minus 2. So we would like to subtract equation 2 from equation 1. If we have a look at the terms, what this will amount to is that some terms will cancel out. For example, this term will cancel out. Just like this term will cancel out. This is very neat because at this point we can rewrite this expression as a zeros will also cancel out, so we can cross these out as well. So this expression is going to be a1 times, well, these cancel out because we have a1, these terms are there in both expressions. Minus is going to give us minus 2 sine omega x sine omega s plus b1. So in the second term, we will have b1 times cosine sine. Minus will give us a plus cosine sine, same terms. So we will have 2 times cosine omega x sine omega s. So this is going to be the difference between equations 1 and 2. Let's make note of this result because we will be using it. All right, so we previously obtained an expression for when we subtracted the second equation from the first equation. Let's rewrite that. You can see the result that we've obtained on the screen right now. Let's rewrite it. What we were writing up is essentially the expectation value where we are inputting x plus s minus the expectation value where we are shifting into the negative direction with s. What we can do here is, if we look at the expression that was on the screen, is that we can move some of the terms into the denominator here, making this be divided by 2 times sine omega s, and making this be equal to minus a1 sine omega x plus b1 cosine omega x. At this point, let's consider the third equation, which is going to be the derivative of ex. Well, looking at the form of ex that you can see on the screen right now, we can perform the derivation, compute the gradient just naively. The derivative of cosine is going to be minus sine, and the derivative of sine is going to be cosine. So what we obtain is going to be minus a1 times sine omega x plus b1 cosine omega x. One thing that is missing so far is because of the chain rule, we will get a coefficient for both terms. So what we can do is we need to basically multiply this by this omega that came out because of the chain rule. This is going to be the derivative of Ex. Well, if we compare the third equation with the equation that we've derived here, well, on the right-hand side, we actually have just the expression that is within the square brackets here. So let's substitute that expression in here. What we will get is that the derivative of the expectation value Ex is going to be Ex plus S minus Ex minus S times omega divided by 2 times sine omega S. This is the two-term parameter shift rule. This rule can be used for some special gates, and in this case, we can choose this S arbitrarily within some constraints, as well as we usually know what the value for this omega is going to be. As you see, once we have a Fourier representation of an expectation value, deriving the two-term parameter shift rule can be done manually and quite fast. And the Fourier representation will also be useful for other parameter shift rules that are not applicable to special gates, but require a more complex form to be written. Let's also note that for most gates, what we will have in this case is going to be omega is going to be 1. We can also just pick S to be pi over 2. And what this expression will then be simplified is going to be 1 over 2 times Ex plus S minus Ex minus S. This might be one of the representations that you've seen for the two-term parameter shift rule. And this is one of the first appearances in literature as well for the two-term parameter shift rule in the paper from Mitarai and others that was written on quantum circuit learning. At this point, we will also just show you an example for using the two-term parameter shift rule using PennyLane through a code example.
Hey, Isaac here. Let's demonstrate a real-world example where the two-term parameter shift rule applies for calculating the gradient of an expectation value. Now it turns out that the single qubit rotation gates like Rx, Ry, and Rz have a two-term parameter shift rule. Let's look at the case of the Rz gate. The generator of the Rz gate is the poly Z operator multiplied by -1/2. If we look at the generator matrix, clearly we can see that there are two eigenvalues. One is -1/2 and one is 1/2. These eigenvalues in our notation are called lowercase omega 1 and lowercase omega 2. Capital omega, this set of positive unique differences, in this case is only going to have one element in its set, which is just omega 2 minus omega 1, which in this case is just 1. When we have a set of positive unique differences that has only one element, the two-term parameter shift rule applies. Let's actually verify this result by calculating the expectation value we're interested in. To make sure that we're using the parameter shift rule under the hood in PennyLane as opposed to any other differentiation method, we can specify diff method equals parameter shift when we decorate with @qml.qnode. The operator we're interested in taking the expectation value with respect to is the poly Y operator on the first qubit. Now let's say we want to evaluate the circuit at pi over 12, and the shift value we'll set is pi over 2, since sine of pi over 2 is equal to 1. And finally, when we use the qml.grad transformation on our circuit to calculate the analytic gradient under the hood in PennyLane, and we compare it to our expression that Antal derived, we get the same answer. Nice.
Thank you so much for tuning in for today's video. This was the video on deriving the two-term parameter shift rule. Hope to see you in the next video. Take care.